All right, everybody, good morning. Welcome back to Machine Organization and Programming. Just a couple of announcements as we get started. First, Project 4 was due last night. Only 61 students out of the 85 have turned it in so far. And I did get a record number of requests for extensions due to illness. So we've got at least 5 people who are not doing very well as far as their health goes. Please keep them in your back of your mind. And with that in mind, it's pretty clear that P4 was really a challenging project for a lot of students. I was just overwhelmed with emails, and office hours were full every single day this week. We're not going to start grading this until Monday. And please remember that my late policy is that it's not late until we actually start grading. So if you have more work to do, or if you didn't quite finish it, you're welcome to submit as many times as you like. Just keep turning in a new version every time you make an update. We will grade the most recent on-time version of your project. All right, then a little bit as far as the schedule goes. Today we're looking at the second part of dynamic memory allocation. Later this afternoon, I'll be recording a video on cache memories. And then next week, last week of class, we're going to wrap up with some videos on operating systems. The final project, Project 5, will be released this afternoon. That's going to be due 1 week from Sunday. That is the last moment of class, is Sunday evening, August 7th, I think. And then we will have a quiz on Monday, just like normal. It's going to be available Monday through Wednesday. And let's see, last up, a final exam will be released next Thursday. And that again will be available all the way through Sunday at midnight, the last possible moment of class, to give you guys as much time to take it as possible. I wasn't originally planning to release the final exam this early, but I do have a couple of students who have requested that the final exam be available, so I'm just going to release it early. You have still 4 full days to take it, so I think that'll wrap up the announcements. Okay, next up. So we were talking about dynamic memory allocation, and just a little bit of review to remember where we are. So dynamic memory allocation is when we want to reserve some memory for our program on the heap. We may not know how much we need ahead of time. We may need a huge block of memory. And dynamic memory allocation lets us just say, Malik, give me a number of bytes right there on the heap, and I'll take care of it. The heap is generally much larger than the stack, so we can hold larger data structures, and I don't need to know ahead of time how much memory I'll be requesting. So that is all controlled by a memory allocator. All of that, where do I get the memory, how much memory is available on the heap, all that's taken care of by a memory allocator. Malik is an example of a memory allocator. But we'll see that a lot of software actually writes their own memory allocator to take care of this themselves for performance requirements for their particular application. Okay, so memory allocators have a number of requirements that we need to meet. First, we need to keep track of how big all of these allocations are. We don't need to remember where they are because we're giving the user pointers, and it's their responsibility to keep track of that. So when they free it, I need to know how many bytes to free. We're also going to see that the requests for memory can come in any order. I'm not allowed to buffer them or reorder them or deal with that to improve performance. I can only use the heap. I'm not allowed to use the stack to keep track of this information. I'm going to have some very specific block alignment requirements. We'll review those in a second. And finally, once I've given the program some memory, I'm not allowed to touch that anymore. That memory is reserved for the user, and I can't go back and say, well, it'd fit a lot better if I moved it over here. Can't move it. I don't know how many copies of pointers they've made to that same memory, so can't touch it. Okay, so we started talking about implementation issues last time, and the first part was just how do we track how big these allocations are. And we were looking at using an implicit free list, so I'll review that in a second. So we need to just keep a list of how big these things are, so I know how much memory to reclaim when the user frees a particular pointer. And so the other 3 issues that we're going to talk about today, just to introduce these ideas, are different placement policies. So once I've got the heap, I've been using it for a while, I've been giving away memory, I've been freeing it again, I'm going to have a chunk of memory where pieces of it are used and pieces of it are free. And I need to decide where am I going to give the user the next block of memory. Basically, is it going to come from a block that's really fast for me to find? Am I going to try the exact best fit? Or a couple of other versions we'll talk about. When I do find a hole in the memory big enough for my allocation, then looking at point 3 here, if it's too big, I'm going to need to split that chunk of free memory into a part to give to the user and then the remainder to save to give to the next request. We'll talk about different splitting policies. And finally, when a user frees some memory, so this is sort of the reverse of that. If I've got an adjacent free block next to the one that I just freed, the idea is I want to, rather than keeping 2 small blocks next to each other, I'd rather have one big block that I know is free. All right, so let's take a look at this idea of a free list. So the idea is that for every block that I've given to a user, the green payloads over here, like this 4-byte allocation at P1, is going to be prefixed with a header. So the byte right in front of the memory that I've given to the user, I'm just going to use that to store some information about how much has been given away. So that way when the user comes back and says free P1, I can go and look and say, oh, it was 8 bytes total including my header, and so I can just mark this region of memory from byte 4 to byte 11 as now available and free. So that's the idea for the very simple free list. So let's just walk through an example real quickly. So this is actually the example I used for my last lecture, so you can fast forward a little bit if that totally made sense and you feel like, I don't need to review this. But so the initial state of the heap is going to have, all right, real quick, we're going to skip using the very first byte in this particular version because I'm using an 8-byte memory alignment requirement. So that means my very first pointer that I can give to the user needs to fall on a byte that's divisible by 8. So either 8 or 16 or 24. So this block right here where the mouse pointer is will be the very first block that I can give to the user. And so that means the header needs to fall in the block right before that at byte 4. And that means there's always going to be 1 byte at the very beginning that's unused with this particular model. With the 8-byte memory alignment. If it were a different alignment requirement, if it were 16, then I would have 3 bytes unused at the very beginning. First payload block would be 16, the header would be at 12 with 3 unused. Okay, so then when the user says, give me 4 bytes, I'm going to go ahead and give them 4 bytes right there. Oh, I forgot something. So the initial header is going to have all the possible bytes, and they're going to be marked as free. So 0 is free. 56 is the total size of my heap right now. That's the remaining bytes in this block. So take away so I've got 64 bytes here. Take away the 4 that I'm using for my unused block right there, leaves 56. All right, user comes and says, give me 4 bytes, please. So payload is going to go at byte 8 to match with that memory alignment requirement. I'm going to go ahead and change this first header and say, okay, I'm now using 8 bytes. They are used. That's what that 1 is for. That's the alloc bit. 8 bytes being used, so that's 4 for the header, 4 for the payload. And then we're going to add another header down at the very next byte below that payload, potentially with some padding, because the next available byte to be given to the user will be at 16. But this is going to now be reduced by 8. So it had been 56. We're using 8 for this payload and header. So 56 take away 8 is going to leave 48 bytes left. Okay, when I come to the next request, it's going to do the same thing. It's going to go and say, find a place for it right here. In this case, I'm now going to allocate 16 bytes. Here's the idea. The payload is going on byte 16. I need 8 of them, so there's 2 blocks. But the next available allocation is going to be coming at 32 because it needs to be divisible by 8. The header for that is going to go on 28. And we'll have an unused block here at 24. So that's just going to be padding as a requirement for the memory alignment that we talked about. All right, so we changed this header 16 now because that's 1, 2, 3, 4 times 4 because each of these are 4 bytes. And we'll mark this as used. Then change the header. So I had, 48? Take away 16 leaves 32 bytes left. This is all still free. And then finally, if I finish my example by allocating one more byte, just a quick example, this is just going to take up 1 byte. It's going to fall at 32, but then I'm going to have a bunch of padding. In this case, 3 bytes of padding. The header is going to say this is going to take 8 bytes. So this is not super awesome utilization of memory. I'm using 1 byte and wasting 4 for the header, 3 for padding. So this sort of internal fragmentation happens quite frequently. And we're going to try and do our best to avoid that if we can with the memory allocator model that we choose, but not always perfect. All right, and then let's see, if we go ahead and free P2, that's going to just, here, let me flip back a second. P2 is right here. I'm given a pointer to the first byte in payload. So when I free it, I know that the header is the byte, or 4 bytes immediately in front of that. And that header is going to tell me how big it is and whether it's available or free. And if I'm freeing it, that means it's being, this bit should be a 1. And all I need to do is flip, where's the mouse pointer, that bit to a 0 to indicate that this block of memory is now available. And all 16 of these bytes, we're not going to change any of the data in the payload here or the padding. Whatever is there is just going to stay. But this is going to get returned to a 0, and that means they all switch back to blue, and we are good to go. We can reuse those. All right. One thought that I'm pretty sure I forgot to mention this last time. I just made one more slide for this. How do we know when we get to the end of the heap? This works a lot like a linked list, where each header tells me where the next one starts. And I can just keep like traversing this forever. What we're going to find is that they use an end of stack marker, which is just a header where we've given 0 bytes as the length to the next available block of memory, and it's indicated as used. So this 0, 1, and this is basically just in binary, it's all zeros except for the final bit that's a 1, means this is the end of the heap. You've reached it. Return failure if your like placement policy says that you've checked everywhere and haven't found a place. So we'll talk about placement policy in just a sec. Real quick, quick review of what these headers look like. I get 4 bytes to do this, and I've got a 1 or a 0 that I need to do. So 4 bytes for the size of the payload that I can have, plus the header and any padding. And then the other bit is just whether it's allocated or not. So I'm going to pack these in. And the key to remember here is that because of this alignment requirement, all of the sizes are actually going to be multiples of 8 also. So, and what that means is that the last 3 bits of anything that's a multiple of 8 will always be 0. So I've got 3 more bits available that I can use to store meta information. And so that 1 or 0 is just going to be used as the B0 bit. So if it's free, we'll see that this is a 0. And again, 8, 0 is going to be 8 blocks that are free. If it's a 1, then it's been allocated. So sort of an odd-even test. So odd numbers mean that we've allocated them. Even numbers mean that they are available. So just a quick review on that. And we still have 2 more bits. We'll come back. We'll see those are used for something later. All right, let's just take a look at an example of a memory that's got some places available. We'll talk about how the free list is actually a list. And then we'll talk about different placement policies. So these are kind of blend together into a smooth transition, I hope. So here's the idea. If I've got memory that's in a state that looks like this, where I've got 2 available blocks, so there's one here, there's one here, and some used blocks, 1, 2, and then it just continues on down there. I have only drawn the beginning. So the idea here is this is actually, so I'm going to be looking at 2 requests. First we'll grab 4 bytes and then we'll grab 12 bytes. But this actually works a lot like a linked list. So the idea is I'm going to search through the entire heap and find a good spot for that. Well, the first one was a 4 byte allocation. And all of these headers, because they're in, they just tell me how much space is used up by the payload and the header, mean that 16 bytes from here, so this is at byte 4, looking at the very first header, 16 bytes from here I'm going to find the next header. And it's going to tell me how big this block is and whether it's available or free. And then this one, 16 bytes from here, so 20 plus 16 is 36. I jump down to here. this is going to tell me how many bytes are available in the next block and whether it's available or free. Sorry, I misclicked there. So this essentially works just like a linked list. This is a pointer to the next one. It's a relative pointer because I need the current address where I'm at. I just add that number to it, and that gives me the next one. Add this number, gives me the next one. Add that number, the 16. That's going to give me the next one. All right, so hopefully that's clear. It's just a way to traverse all these blocks. I don't have to read every single thing. I don't have to worry about whether it's payload or header. I know where the first header starts, and then I can just make jumps. So the more blocks I have with this sort of implicit free list, the longer it's going to take to search through the entire list. All right, yeah, and then, okay, placement policy. So if my placement policy, we're going to talk about 4 of them. The very first one is called first fit. And this is just going to say start at the beginning of the list. Start with header number 1. I've got 16 bytes. This one's taken. So jump down. And in the previous example, the next block there was free. I've already drawn it in the picture with that 4-byte allocated placed in there. So we found a block where it fits. It'll be right there at 20. And then first fit says just find the first block where it fits and stick it in there. So this is going to result in splitting. So I have my header here that's telling me I'm only going to be reserving 8 bytes total, 4 for the header, 4 for that malloc. And then this next piece is going to be the remainder. So I had 16, I used 8. That means there's 8 bytes left. That is just going to be a new header placed at byte 28. And this is going to be free. So this is the idea of splitting. I'm going to come back and talk about different splitting policies in a moment. But first, just to motivate this a little more as I finish talking about placement, this is going to be successful. We're still going to have this like fragmented piece here. It's going to split it into, a used block and a small block. And then my next allocation request is for 12 bytes. Now check this out. I do actually have 12 bytes available. There's, 1, 2, 3, 4 blue box. It's a little deceptive because I've actually got 2 of them listed as headers. If they were together though, those 4 boxes, 1 of them would be header and 3 of them would be free if they were adjacent to each other, if they were contiguous. So I do have enough space for this, but my first fit policy says I'm going to start at the first header, jump down, and try and find a header that actually has, it's going to say 16, 4 for the allocation, for the header, and 12 for the allocation. So that's all I'm going to do is look for a 16 free or something bigger than 16. And this is going to fail. All of the available blocks are too small. I've got room for a 4-byte allocation here, 4-byte here, but not 12. So this is going to be when malloc returns null, and it's important you check to make sure that malloc actually returned a valid pointer. So, yeah, remember we are not allowed to reorder these requests. This would have worked if I go back here, if I'd had the malloc 12 first, it would have fit right here. That would have worked. And then the 4 would have fit right here. So I did 12 and 4. If I'd switched the order, it would have worked. But that is not allowed. I cannot do that. All right. So some just characteristics of a first fit placement policy. We're going to see that, because we're searching from the beginning every single time, what it's going to do is sort of cram everything into the beginning if it can. And what we're going to see is that it's going to fragment the beginning of the list. In fact, right here is an example of that fragmentation where I left behind what's known as a sliver, a free block that's really too small to do anything with. We're also going to see that the large blocks of free memory are going to be available toward the end of the list. So if I have a lot of allocations, I'm using it, I'm allocating, I'm freeing, and then I get to a place where my web browser wants to store a really large image or something like that. I need to reserve a lot of memory. It's got a long search to get to the end of the list to figure out where to put that. And because of this, always starting from the beginning, it's going to increase that search time as I need to work my way toward the end of the list just to find a large enough place. All right, there's another placement policy that's very, very similar to first fit. First fit keeps track of, it doesn't have to keep track of where we start searching from because it always starts right here with byte 4 and then looks through all the headers to figure out where is the next one. Next fit is going to keep track of where did I put the last allocation. So in my example right here at block 20 is where I stored that malloc 4, right there. And so it's going to just keep a pointer that points to block 28 in this case. And when we do next fit, it's going to start searching from block 28 for the next allocation. So some of the characteristics of this, it's going to be faster, likely to be faster, particularly during the beginning of a program's lifetime when there's lots of memory available. It doesn't have to start searching from the beginning. But what we're going to find also is that the memory allocation is not quite as good. The first fit tends to find a spot near the beginning where things fit, and those places tend to be smaller. And so it's more likely that when I allocate something, it's going to be in a block that's very close to the right size. And it's rare that it gets to the end and uses the block that's much bigger and splits it. The next fit is going to start searching from somewhere in the middle of the list and doesn't enjoy that large blocks at the end are available, and instead fragments those a lot more uniformly. So first fit leaves big blocks at the end, little blocks at the beginning. Next fit is more uniform, and we're going to have fewer large blocks and fewer small blocks, more medium kind of like spaces, holes available for allocation. Okay, next up, the best fit. You'd think this one would be very good, and it is. A lot of memory allocators used best fit. The idea is that every single time I allocate something, I am going to search the entire memory, the entire heap, and find the absolute best block. I'm looking for the smallest block where my allocation will actually fit. What we'll see is that we get really good memory utilization. If I have a block that's exactly 16 bytes available and I try and find the a place for 12, this totally works. Here, let me scroll back up to this example. So in this case, when I called malloc of 4, it's going to search. It's going to start right here at block 4. It's going to see 16 bytes later. Ooh, this would work. It would fit. But I'm going to keep searching and see if I have another block that would fit even better. So I go from byte 20, advance by 16 here. That one's used. We skip it. We advanced again. And as soon as it finds one that's an exact fit, it'll go ahead and put it in. So here I've got 8 bytes. I'm looking for 4 for the header, 4 for that allocation. It fits. It would have put this right here. And then best fit would go back and say next allocation is 12. I'm going to just start searching right here from byte 4. That one's taken. Can't use it. Advance by 16. Finds this block. 16, 0. That's perfect. 4 for the header. 12 for the allocation. It would stick that one right there. So best fit would have dealt with this example easily. All right, let me scroll back down. Okay, so it searches the entire memory for the absolute best block. Because every single time it's searching through the entire heap, this tends to be slow, but result in excellent memory utilization. Some of the issues that do develop with this best fit model are that it tends to leave really small fragments behind. So if I'm looking for a block that's 1,000 bytes, and I happen to find the perfect block that's 1,008 bytes, it's going to leave behind a really tiny fragment that is only going to be good for 8 bytes worth of 4 after the header. And so what we see are it leaves behind blocks that are almost unusable, except for if I just have one character I want to allocate on the heap. All right, and finally, our book doesn't even talk about worst fit, but I think from an analysis point of view, it's useful to talk about worst fit and look at what advantages that it does have. I don't think I've seen any memory allocators that ever use it, but they're probably out there. I just don't know. The idea here is that we're going to find the largest block available in the entire memory, the largest free block, and that's where we're going to put all the new allocations. The advantage here is that it doesn't leave behind small fragments. And the idea with that is it's going to maximize the chance that the next allocation will actually fit. Now, as soon as I like use the heap a lot, I'm going to find that I'm left with smaller and smaller large blocks. I mean, the large blocks are always used. The next largest block, every time I allocate something, is always going to be smaller, but it's going to leave behind the biggest possible holes. So if I have, if I rarely need to allocate a really large piece, if most of what I have is quite small, this does work very well. All right, next up I want to talk a little bit about block splitting. So there are basically two different versions that we'll see memory allocators choose. Consider the heap in this state right here. And now if I want to allocate just 4 bytes, if I'm choosing this larger block with a first fit model, I've got a couple of choices. I've got 16 bytes available. It's going to take up exactly half of this and leave behind a 4-byte sliver, something that's quite small. So we'll see that memory allocators have choices here. They can either choose to split this and go ahead and leave that 4 bytes available for the header there, and get a little tiny splinter plus whatever the user requested. Or the other choice is to just allocate the entire block. And most memory allocators have sort of a minimum size splinter that they're willing to leave behind before they just allocate the entire block. And what we'll see is what that's going to do is it's going to waste some memory. If I take my 4-byte allocation and then give it these extra 8 bytes here, it's wasting some memory. So memory utilization is less good. But what it does is when I create that linked list and I've got to search through the entire list for a new space, it's going to keep the size of the list smaller, because instead of having an 8 header and an 8 header here, where I'm likely not going to be able to use that one, it'll just keep one header, and it'll be 16.1. So the jumps will go to there and there and there. So the linked list is short. I have to search through less stuff to allocate the next block. And this is going to minimize those splinters that I need to search through. The other choice is to split the block. And I really have two choices here as well. If I wanted to split this, I could put the memory, allocate the new memory at the very beginning, so byte 20 right here, or I could allocate those 4 bytes at the end, put the header here. So begin with the header at 28, leave this block free, and occupy this one. Some of the advantages here are that as I'm searching my linked list, if I put the allocation at the end, then I'm going to get to this free memory sooner. Disadvantage that if I want to call realloc, I'm going to have to move this entire block and provide a new pointer somewhere else because the next block is taken up. And the final issue that we'll see in just a second is that if I'm using this philosophy that, or my best guess is that as I free things, they're going to be freed in the order they were allocated. So right here, this block of memory is free. This one's older, and the one behind it is older. So it's likely that those will be freed first. And it is much, much easier to merge blocks behind, so at bigger memory addresses, than it is to merge earlier ones. So, and we'll see that with coalescing in just a second. So if I actually take block 28 and 32 for my new allocation, and then I free this one, coalescing that to make one large free block is much easier than if I use the beginning of this memory block and stick it right here, come back, free this one, and then when I free this one, merging that together is a lot more difficult to merge something that occurs previously in the list. Let's see. I think that does it for splitting. Let's jump into coalescing here. There's two different versions of coalescing we'll see. Immediate coalescing. Hold on one sec. The little guy's coming down. All right. Got him all taken care of. Where was I? Coalescing. Okay. Now there's two different versions of coalescing. Basically, coalescing is going to mean that I'm going to take two adjacent free blocks and turn them into one larger free block. And with a larger header. It's going to leave behind larger holes that I can then use to fill in. We have two different versions here, immediate and deferred. Immediate is going to happen every single time we call free. It's going to check to see if there's an adjacent free block and then merge those guys together. Deferred coalescing is going to be called less frequently. You can imagine as soon as the memory allocation fails, or it takes too long, we're going to go through and say, okay, it's time. We're going to go through the entire list. We're just going to hop from every block to every block, find blocks that are next to each other, that are, two adjacent blocks that are free, and we're going to merge them together. All right, we'll see that a combination of these is frequently used in real memory allocators. And just as an example, if I call free with this heap for P1 here, and so that's obviously going to give me the pointer to the payload. The header right in front of it tells me that this is allocated. So when I free that, there we go. I'm going to just flip this bit to a 0. That's going to turn this back to blue, make it available. But now I've got two small free blocks next to each other. When I have free blocks adjacent to each other that are smaller, this looks like fragmentation. It's known as false fragmentation, even though I do have like 16 contiguous bytes that are available. My headers system says I've got 4 bytes here and 4 bytes here. So that's false fragmentation. The idea of coalescing is I'm going to go ahead and recognize immediately that I've got, so when I freed the number 20 right here, immediate coalescing is going to say just jump down 8 more bytes and check this out. If this is also free, then we can just merge those together. Oh yeah, I actually made a slide for this. Use the arrow, follow it down, verify this one's actually free, and then we can merge them together. So that idea is known as coalescing, and this is an example of immediate coalescing. It's really easy to merge with a free block that's at higher memory addresses, lower in my heap right here. If I want to do the same thing, so jump back, but in this case, I'm actually going to be freeing the block below this. So I'm going to go ahead, flip that to a 0. It's now free, but I have a really hard time trying to figure out if the previous block is free. So I've got this byte, this block of memory was 8. I've got a pointer here that goes to the next block, but I haven't stored anything that goes to the previous block. To figure out if I can coalesce these two blocks after I free one, I basically need to start at the very beginning of the heap and jump down and try and locate the block in front of it. With this is with that very simple implicit free list model that I was using to keep track of just how many bytes are available in each allocation. So that's a lot more difficult to do. We'll talk about a strategy. Oh yeah, I made a slide for this too. So there's no pointer that goes backwards. So I need to go through the entire list. And this might be a great place where I just want to say, oh, I'm not going to bother searching the entire list yet. If I have to search the entire list, I might as well wait till I've got a bunch of adjacent free blocks and just merge them all up at the same time, which will be more efficient because then that just involves one traversal of the list rather than one every single time I call free. All right, just one final example. If I'm freeing a block here at like 36, where it's got a free block in front of it and a free block behind it, I may choose to use sort of a combination strategy. So let me see, if I free this, then I've got 3 adjacent free blocks. This might be a good opportunity to use the immediate to just merge the 16 here and the 8 behind it, because that's really easy. And then come back later when I have a memory allocation fail and then merge the 8 in front of it, because that's a lot more work. Another option is, say I do have 3 blocks in a row, so traversing the entire list, I don't need to do anything special. I'll automatically grab all 3 of those and merge them into one larger block. Okay, and to wrap up this kind of idea, in order to make it much easier to find the block in front, we can just store metadata, a little bit of extra metadata, to help keep track of, basically a pointer to the previous block. This number, the size here, is basically a pointer that points to the next block. All we need to do is record a little bit of extra information. And this idea is known as boundary tags. So I've got 2 versions of this. We've got beginner boundary tags and advanced. So here's the idea. For every block of memory that I allocate, I'll have a payload. It's going to return a pointer to that payload. We've already learned that in the previous 4 bytes, we're going to be storing a header that keeps track of the size so that I can free it and I can use that to find the next block. But we'll also go ahead and make a copy of that same header after the allocation. So this is going to use an extra 4 bytes per block because I need to track that extra meta information, known as a footer because it's at the end of a block. But it's going to be the exact same size, the exact same alloc bit. And then when I come back, if I take a look at, let's see, did I make a slide for this? Yep. If I call free for block P right here, it knows where the header is. It can find the next block, and then we can check to see if this is allocated or not. If it's free, then we can merge these two blocks together. The 4 bytes immediately in front of that header, or 8 bytes away from P, is the footer for the previous block. And this is going to give me the size of that. So if I know this block is 16 bytes, it'll be 16 right here, 16 right here. And that means I can jump from this from my header, go backwards 16 bytes to get to the header for this one. And if this is available, if this is a free block, then I can merge this block, header 1, or block 1, with block 2. So this is going to, it's worse for memory utilization because I've got to keep extra metadata, but it means that I can coalesce blocks that are adjacent either with the block in front of it or block behind it in constant time. It's just immediate. I don't need to search the entire list. That depends on how many blocks I have allocated and free, the total number of those. So it makes that much, much faster at the expense of extra memory. Let's see, did I get all my notes here? All right, the next idea is known as improved boundary tags. So this is going to take advantage of the fact that I have those 3 bytes at the end of every size. Every header has 3 bytes available because they have to be multiples of 8. So the last 3 are going to be 0, 0, 0. We've already used the B0 bit to indicate whether this block, is, a particular block is allocated or free. What we can do is we can take the next one over, the B1 byte, and use that to say, is the previous block allocated or not? All right. And then if it's not allocated, if it's actually free, then I know that I need to go back and check it out. So the idea here is that instead of putting a footer on every single block, I really only need footers on the free blocks. And I can use that extra bit in the header of any particular block to say, is the block in front of it free? If it is free, then I know that the footer is there. So all free blocks have footers. Blocks that are allocated just have payload. They do not need a footer because nothing will ever get merged with them. I'm not going to merge with something that's already used. So, like for example, if I free block 3 right here, it's going to have that B1 bit of the header say that the previous block is occupied. Don't merge with it. So I can just skip that. If I'm looking at block 2, however, that bit is going to say block 1 is free. That means there's a footer here, basically a pointer that I can use to go get to the beginning of block 1 and then merge that together. So we'll see in this particular model, we get slightly better memory utilization because I don't need to store a footer for any block that has a payload. And I already have that B1 bit available that I wasn't using before. So that doesn't take any extra memory. I was just already wasting it. So I'm taking advantage of memory that was previously being wasted. It is slightly more complicated as far as the instructions required to just check and see if the previous block is free or not. But it does give us the constant time coalescing. I don't need to search through the entire list to figure out whether it's there or not. All right, I think this is my last slide. Yep. So next thing, what I want to do is just do a couple of examples where we're just going to do some experimenting on the CSL computers and see if we can figure out what we can learn about how malloc actually works on those computers. One second, let me go pull that up. All right, guys, I just put together a real quick experiment. All I'm doing here is I'm going to be mallocing exactly 1 byte, just a bunch of times, and then I'm going to print out the memory address where it's given me those allocations. So pause the video, stare at that for a sec if you need to, and I'm going to, like that. So I was testing this a moment ago. I already compiled it. Now check this out. Here's the idea. P1 is stored at, let's see, that digit's the same, that one's the same. 4. Okay, so I can ignore the first bunch of digits. It's 1A0. The next one's stored at 5C0. Check this out. So I did some math real quick. I just took, by the way, Google Chrome does math in hex for us. So I took the second address, 5C0, subtracted 1A0, and found out that we're looking at, in hex 420. So real quick, hex 420 to decimal is going to be 1056 bytes. All right, so interesting. So it's reserved 1 byte here, and then the next allocation is actually 1,000 bytes later. But check this out. From there on, P3, P4, we're actually going from C to D to E. So this is just incrementing by 16 bytes. So this is telling me that the memory alignment requirement, and basically I'm looking for the smallest possible number here to get that memory alignment, is going to be a difference of, in hex 10, or the decimal 16 bytes. All right, let me set up my next experiment so you guys don't have to watch me type, and I'll be right back. All right, got my next example all set up, ready to go. So I retained all of this, and then all I did was in a loop. So I figured out that in this first experiment, that sort of the memory alignment requirement is 16 bytes. So I'm just going to scan through, beginning with size 1 up to 16, and malloc, first 1 byte, then 2 bytes, then 3 bytes, then 4 bytes. I'm going to reuse that same pointer every time, and just print out the memory address where it's giving me that allocation. Rewriting over that pointer in general would be bad, because then I totally lose the ability to free it. I'm going to just not worry about it right now, because it's just an experiment. All right, quit /a.out. All right, so when I run this, what I'm looking for here is it's going to count up by 16 bytes. So from F to 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Ooh, there's no 10 though. Oops, A, B. Wait, there it is. There's no C. So this is the byte right there. As soon as I have allocated 13 bytes, it suddenly is going to, so this one right here is the first one, the 13 byte allocation, where I now require 2 of those, 16 byte block aligned segments. So that's telling me that I can allocate 12 bytes and it's going to fit into 16 bytes, because the next one was given to me 16 bytes later from A to B. But as soon as I try and grab 13 bytes, it needs more memory. So this is suggesting that I'm using that very simple, what's it called? Free list, implicit free list model. I don't know about boundary tags, if I'm putting a footer for free blocks or not. Let me see if I can think of an experiment that'll highlight whether this is using that or not. One sec. Now guys, I actually thought of a slightly different experiment that I want to try first. I made a minor change here. So instead of reusing the same pointer over and over, and generally bad practice, I'm instead declaring an array of 20 pointers to integers. Okay. Next, after that, I'm going to be allocating, well, the first 16 of them has plenty. I don't know why I picked 20. Anyway, here we go. For each of those allocations, I'm just going to allocate, 1 byte, then 2 bytes, then 3 bytes. I didn't change that. Print it out again. I'm just switching to an array so that I could fill in lots of pointers and retain them. Then I'm going to go back and I'm going to free one of the pointers. I just grabbed P2. It seemed like a good idea. It's at the beginning. It takes up 16 bytes. It's not the first one. It's in the middle of that list. So we'll free that one. I made a note. It's going to print that out to let me know I've done that. Little reminder. Then I'm going to declare a brand new pointer, and I'm going to see if this goes in that spot that was freed by P2, or if it's going to follow like a next fit kind of model and place it at the end. All right, so this is an experiment to see if it's going to search for the best fit or the first fit. No, next or first. Okay, so anyway, it's just going to malloc 1 byte and then print out where it is. Yeah, that's the idea. Save that. Then we will run this and take a look at the results. Okay, so F012. So P2 is at that address right there. Takes up 2 bytes. Now, when I go down, I free P2, and then I declare a new pointer. Is this memory address 50600, 50600? It is indeed the same place. So that would imply that this is a first fit model, potentially best fit. So we can go back and experiment with that in just a second also. But it's not using the next fit because then it would have been one address after that one. All right, one more experiment. One sec. All right, guys, I put together an example that's going to help us decide whether malloc is using a best fit, first fit, or first fit model. Here's the idea. I've just gone in this block right here, gone ahead and declared 1, 2, 3, 4, 5 pointers, given them all 12s except for this second one. I wanted to make the second one much larger. So as the memory allocator is scanning through, it's going to, well, and then I free the second one and the fourth one. It's going to find a large free block, but then there's a smaller free block later. And then if I'm mallocing after I've freed those 12 byte block, will it put it in this 44 sized hole? That would be the first fit. Or will it find this exact best fit 12 a little bit later? All right, so that's the idea. Let me get out of here, and then we'll run this. I already compiled it. All right, so down at the bottom here, we see that R1 is going to be at 710, 720. This is going to be a larger block, so 750, 760, 70, 70. All right, and then I'm going to free the second one and the fourth one. So those two, so I've got a large hole right here. And then when we do one more allocation, if it's first fit, this will give us a 720. And if it's best fit, it'll give us 760. And what we see down here at the bottom is that R is actually stored at 760, which would imply a best fit model. All right, that's going to do it for me today. Remember, please go turn in Project 4. Project 5 will be released as soon as this video goes up. Maybe within an hour. Got a little tweaking to do. All right, but have a great day, guys. I hope you enjoyed this, and look forward to putting together that cache memory video.